Okay, let's start. Hello, everyone. This is Adel. Welcome to the sixth internship guidance session in production discipline titled Well Modeling, presented by
Okay, let's start.
Engineer
Hello,
Ahmed.
everyone. This is Adel.
Presented by Engineer Ahmed Gaber. Engineer Ahmed Gaber is a senior petroleum engineer with more than 13 years of experience. I will let him introduce himself better than me. So, Engineer Ahmed, you can open the mic and start your presentation.
Hello, everyone. It's a pleasure to be with you today. Actually, this is not my first live streaming with or internship with OPA, and it's a pleasure to be with you and with them all the time. My name is Ahmed Gaber. I'm senior petroleum engineer with more than 13 years of experience. Actually, I can divide my career path into two paths. Part of my career, I was responsible for production optimization and production technology, where I was responsible for well modeling, um, initiating the well works, review the wells, networks, and other parts where I was responsible for the well intervention parts in my company. So today, inshallah, we will go through the well modeling and we will make a quick review about the nodal analysis and how we can do well modeling using Prosper model. And then we will talk also about some pipe sim and some differences between the Prosper and the pipe sim. So I hope you all enjoy and we gain knowledge from each other. I will start sharing my screen. So please, can you tell me if you can see my screen all?
Yes,
Anyone
yes,
can?
we can see.
Okay, okay. So let's start with a question. Why well modeling? What is the benefits or what is the advantage of doing well modeling? So in well modeling, you can predict the performance of the well. For example, I have a well and the current reservoir pressure is 2000. Then the reservoir pressure decreased. It's now 1000. So I can predict how will be the well production rate. Another example, for example, I have a problem in the separator and I have to raise the pressure of the separator. So I will have to raise the tubing pressure. So I want to know or to predict what will be the new rate. Another thing is that, for example, I have a well and I have to drill this well, and I want to know, is this well economical for drilling and completion or not? How can I do it? I can do it by modeling the well, and from the well model, I can predict what will be the rate or the initial rate of the well based on, as we will see, based on the data that will be taken from the reservoir engineer, from the completion engineer, from different discipline. So I can predict what will be the production performance of the well, and I can decide either it's economical or not. Also, I can use the well model itself for doing the completion design. Uh, for some people of you who have already joined the industry or still learning about it, completion, we have many types of completion, and even for a single completion, you have many sizes of the tubing. Okay, you can use a tubing size 4.5, 3.5, 278, different sizes. You can complete the well open hole or cased hole or slotted liner. So with using Prosper, you can put each scenario and you can predict what will be the rate in each scenario. Okay, and based on this, you can decide this scenario with this cost, with this pros and cons, and I can go to this scenario. So Prosper or modeling generally can provide us with this advantage. Another thing is optimizing and designing of the artificial lift. If there is a new one and I want to do the design, sure there are different scenarios or different tools that I even with Excel sheet I can do the design, but it's difficult. It will take some time. For Prosper and for PipeSim and for all models, it's softwares. It's easy. I can do it as we will see with an example. I can do it in no time. And if there exists an artificial lift method, I can optimize it. I can change in the parameters of the artificial lift method to get the optimum production rate. Another advantage of Prosper is investigating the performance. I have a well, and this well is usually it's producing 2,000 barrel. Now it's producing 1,000 barrel, 500. So there's 500 barrel drop. So using Prosper, I can see is this drop is natural due to some decline in the reservoir pressure or changing in the separator or the tubing head pressure or whatever a normal change happened, or it is problem regarding the well itself. This can be problem in the well bore, problem in the tubing, problem in the reservoir. There is a skin, there is damage. So based on this, I can understand what's actually the problem. Or for example, it can be a problem in the artificial lift itself. So based on this evaluation or troubleshooting, I can decide what can be the problem. And based on this, I can determine well work opportunities. I can determine whether I need stimulation or reperforation to improve the productivity index or to restore the production when it's a problem in the reservoir. Or I can, for example, the tubing have scale and it need to be cleaned, so I can clean it. Or another thing that the artificial lift method is underperforming and I need to do some troubleshooting on it. Or finally, I need to work over and pull all the tubing and put another tubing. So both based on Prosper, I can do the or pipe sim or the well modeling, I can do this. And finally, I also can generate lift curves. For example, we have, for some people who don't know it, some wells we have a network. So with in this network, you need models of the well. What is meant by this? For example, I have gas lifted wells, a number of gas lifted wells, and I have a limited supply of gas. And I want to know which wells I open, which wells I close, how many gas it goes to each well. Another example, I have limited power capacity and I need to open certain wells. So these network models, in order to do it, I need models of each well individually, which can be get from Prosper or PipeSim. And finally, the four reservoir simulators for people, for the reservoir engineers, in order to predict how will be the reservoir performing and a lot of stuffs, they need well models from our side. Okay, so this is most of the advantages that we can predict from using well modeling. In order to understand well modeling and go through the model together, we have to review or revise some concepts that we are supposed to know. First, what is the meaning of nodal analysis? Okay, because well modeling is depending on nodal analysis. So as we will see, nodal analysis means node is this point. This is called node. This point, solution node. This is the place where I calculate and where I have a solution, as we will see. So this normally, when we do well modeling, normally or most of the time, this point is at the bottom of our well bore, at the sand face. Okay, so this is called nodal analysis. In nodal analysis, the point above it is called inflow, as we will see, and before it, it's outflow. Here, this part is the part of the reservoir because downhole, let's help to show with this here. Here, this is my node. Okay, so at this node, the fluid is coming from the reservoir. So this is the inflow and the QN is coming from the reservoir. And after this node, this is the outflow. The fluid is going up from this point. So this point is called node, and this is the bottom node. If, for example, I have a node here, so the inflow will be this one, and the outflow will be this one, if the solution or the calculation are here. As we will see, most of our calculations will be here. So this is our node, okay? And normally, the in order for the well to produce, the amount of fluid flowing into the node must be equal to the amount of fluid flowing out of the node. Okay, so this is a schematic of this is the schematic of our system. This is our system. What happens? First, we start from the reservoir. We have a reservoir pressure, and we have our reservoir where the fluid and the hydrocarbon is there moving, then it's moving into the well. And here we have a compilation, different type of compilation. It can be, as we see here, open hole. It can be cased hole. It can be studded liner, whatever. And this is called BWF, the bottom hole flowing pressure. So from here to there, this is a pressure drop called the drawdown. Then the fluid is moving up through the tubing, which is called VLP, as we'll see. As the fluid moving up, it loses from its energy. It loss there is production, there is pressure losses as it's move up until it reach up to the tubing head. And if I have a choke, there can be more reduction in the pressure. Then it moves in the pipeline up and it lose more pressure till it reaches the separator. And in the separator, there can be gas, oil, and water. So the system normally is defined by the end separator. So in some wells, for example, the separator pressure must be 70 psi. So back calculation, the tubing head pressure must be, for example, 100 or 150. And back calculation, you will find the certain BWF that can allow rate or production against this well head pressure. Okay, in other areas, separator can be less or higher. The pipeline's length can be different, which will affect the production losses in the system. So the productivity of the system or the performance is depending on the pressure losses in each area of this system. In well modeling, you are playing with the pressure losses. Simply, you are modeling the pressure losses in each part. I am modeling the pressure losses here, and I am modeling the pressure losses here. And if it's a pipe network, I will model the pressure losses here. Now, our concern is from here down to there. So as we will see, we are modeling two parts, the inflow and the outflow. We are modeling what is the pressure losses with rate in this part and what is the pressure losses with rate at this part. Okay. So as I mentioned, we have two parts or two components, the inflow, which is the movement of the fluid into the reservoir, in the reservoir, from the reservoir to the completion. And this flow through the permeable media is affected by what? First, for example, for sure, the fluid characteristics. For example, we can imagine that if a fluid that is heavy is moving from here to there, it will lose more pressure than a fluid that is volatile or that is not heavy. Okay, so the fluid characteristics will affect the pressure losses from here to there across this porous medium. Light fluid will have less pressure losses than heavy fluid. Less viscous fluid will have less pressure losses than heavy viscous fluid. So the most important is the fluid characteristics, and I stress on this point to show you, as we will see later, the importance of BVT calibration and BVT modeling. Then we have the rock properties. We have a porous media or a reservoir that has high permeability. So the pressure loss across this reservoir will not be the same as a reservoir with low permeability. For example, a 1,000 barrel fluid per day in one well, on one reservoir, may need 500 psi as a drop down here across this part. And for another reservoir, it can need only 100 psi, depending on the rock properties, the thickness of the reservoir, the permeability of the reservoir, and finally the completion design. How is the completion design? It's vertical well, it's deviated well, it's horizontal well, it is open hole, or it's cased hole, or whatever the interface between the well bore and the reservoir. Then we have the second part, which is the VLP, the flow through the casing tubing till the well head. So this part also depending on the fluid characteristics, and this is makes sense, logic, because you are moving a fluid from here up to the surface. If this fluid is heavy, sure it will need more pressure from here, from down to up. It will need more pressure or more energy to go up. Also viscosity is an effect, the amount of gas. All this will have effect. So the fluid characteristics is very important when modeling this part. And you have the completion design, the tubing size, what is the casing size, the deviation, all this. Do I have any chokes or any restriction inside the tubing? Okay. So what I do actually in Prosper or in well modeling, I'm modeling this part and I'm modeling this part. As we see here, the finality of our work is to draw this curve, two curves. This one, I will go to through it in details, the IPR curve, the red one, and the other curve is the VLP. This curve, as we see here, this chart is a relationship between the pressure and the rate. So if we look into the first chart, it shows the pressure at the bottom hole with rate. So let's think about it. In order for the fluid to go from this side to this side, I have to decrease the BWF. Whenever the BWF decreased, means more fluid is coming from the reservoir till here. So normally the relationship between the pressure and the rate for this part, the IPR, the inflow performance, is inversely proportional. For example, and to make it again more obvious, if the pressure here is the same as the reservoir pressure, there will be no movement for the fluid from here to there. But once you decreased the BWF less than the reservoir pressure, then more fluid is coming from here to this side. Until, for example, which is theoretical, it can be achieved, if the pressure here is zero, it will be the maximum flow rate. So this is the IPR, or this is our curve. As I see here at flow rate equals zero, we have the bottom hole pressure equal to the reservoir pressure. Once you decreased the BWF, then you get more rate until you get the absolute open flow, which is the maximum rate. Okay, so this is first part. Then we have the other curve, which is the VLP. VLP, vertical lift performance, or you can say outflow performance, which shows the relationship between the pressure here, the BWF, and the rate for this part. So let's imagine I have a certain tubing head pressure. Let's imagine it's now 100 psi. So as long as the rate from here to there increase, it means I need more energy here to be able to lift the fluid up. So we will find that the relationship between the BWF and the rate along the tubing is directly proportional. As we see, as the rate increase, the BWF also need to be increased. So this VLP is directly proportional, while the IPR is inversely proportional, and the point of intersection is the point at which we have our production rate. Later, we will talk about this part of curve, why it's like this. But normally, I'm starting from this point. As we see, here we have a direct relationship between the BWF and the rate across the VLP, across my tubing and my completion. Okay, in Prosper or on PipeSim, we are doing this. We model this part and we model this part, and then we can get our solution, which is done at the bottom node. Okay, so for the first part, for the IPR, I mentioned for the IPR, it depends on many things. It depends on the fluid characteristics, the rock properties, and the completion design. So before we go through the Prosper and see exactly how we can model it, let's show two things to speak about it. First, in Prosper, we have different IPR models. These IPR models, depending on what is meant by IPR models, how I will enter or input the data into Prosper, and how Prosper calculating the IPR curve, how Prosper is calculating this curve. So as we see, we have different scenarios, different models based on our inputs and based on the data we have. Okay, so for you, suppose that you, most of us, we know that what is the meaning of PI entry. But if, for example, I have data from an offset well, I can get also only a point, which is like the slope, one of the over the slope of this curve. Let's go. PI is the difference or the production rate divided by the drawdown. The production rate divided by the drawdown. So in a certain model, I have this value. I input this value in the model. For example, if I have a test, then I can use a Vogel. If I have more data, I have the permeability of the reservoir, I have the thickness, I have different data, so I can go to Darcy or Vitkovich if I have the relative permeability. If my reservoir is fractured, or if it's, I can go to this model. If I have horizontal wells, I can go to these models. Okay. So as we see here, and we will go to the screen, but I just give you an introduction here. Here, two models, different model. On this model, as we see, sorry, this is the same model. This is the Darcy. As we see, I have the reservoir permeability, the thickness of the reservoir, the drainage area, and all this data, it's available. And I have the skin, so I can model my reservoir using this data, using Darcy. And this is my output. This is my output. I have at the end the PI calculated for this, and the formation PI, and I have the absolute open flow, and this is my model. Okay, so let's open a Prosper model together. So if you open Prosper, you will find that it's very easy. It's like many tabs, and each tabs guide you to the another one. First tab here, you can see its option summary. If I click it on it again, this is first tab, option summary. In option summary, you have to define what is, how will be your model. Generally, how will be your model. So if you look at each tab here, for example, it's fluid description. What is the fluid in your model, in your well? Is it oil well? It's gas well, condensate, water, injector, producer. So here, the fluid description for this well. As we see here, the fluid, it can be oil and water, or dry gas, or retrograde condensate. And as we see in some minutes, you can, how you will model the PVT. You wanted black, oil, or equation of state. And then if you have data, or if you have multiple stage or single stage, if you have emulsion, you want to introduce emulsion or not. If you want PVT warning, the water viscosity, how you will calculate it, and the viscosity model. Okay, so this normally data, if normally you will need to change or to look at the first set, the fluid and the method. Normally, if you have a compositional model, so we will go to the equation of state. If you don't have, you will go to the black oil model. And for the fluid, you will describe what will be your well. It's oil well, or it's a dry and wet gas well, or condensate. Another thing I would like to highlight, what is meaning by viscosity model here, Newtonian fluid. Normally, our fluid will be Newtonian, but the concept of Newtonian and non-Newtonian, it means, 1 second, I bring the, yes. This is what is meant by Newtonian and non-Newtonian. Some fluid, their viscosity are changing when there is a change in the shear rate. For example, you have a fluid, and this fluid, you are moving it with a spoon or anything that increase its shear rate. So if the viscosity is the same, it's called Newtonian fluid. With movement, the viscosity doesn't change. But if with shear rate, it's thickening or it's thinning, for example, the mud is non-Newtonian fluid, because when you move it, it will thin. But if you leave it without steering or anything, it will become thick. Okay, so I wanted to show what is meant by this Newtonian and non-Newtonian fluid. Okay, normally it is the water viscosity, you leave it as it is. or if you have a pressure corrected data, you can use it. And if you have data for emulsion, you can use it. If you don't, you can keep it. If you add here, you will find that in the PVT section, it's added an emulsion data. You have a test and you have, for example, at each water cut, what will be the emulsion. But if you don't have it, so it will kept as no. So as we said, this is the flow description. Then we go to the well. You're defining your well. Is it tubing flow or annular flow or tubing and annular flow? Because there can be different types of completion. You can, for the well, you can flow through the tubing, or you can have flow through the annulus, okay, or mix between both. But normally, most of the time, it's a tubing flow. And as I mentioned, it will be, is it producer or injector, water injector, cool bed methane producer? So what is its type? Then we'll go to the artificial lift method. If it's a natural flow well, then you don't have an artificial lift method. But if it's not natural flow well, so you will go to different artificial lift methods. Whenever we will go through it in our example, but later, whenever you use a certain artificial lift method, then you can go to this method and you can do optimization, and even you can make a design. Then here it's your information. What is the company? What is the field, the location, the well, this data. And then here is what we call calculation type. Are you offshore or onshore wells? If you are offshore well, or if you are onshore well. If you want to calculate only the pressure and neglect the temperature, but I don't recommend this because temperature is very important in our data. Or normally you keep it pressure and temperature and choose what is the type of your field. Then we have our model. It's called, this is for calculating the temperature. This is for modeling the temperature. Why the temperature is important? Because the fluid characteristics are changing with temperature. For example, if you have a fluid which is viscous, with higher temperature, its viscosity will decrease. And viscosity is very important factor because it affects how will be the friction while the fluid is moving. So you have to model this correctly. Because if you didn't model it correctly, you may end with error. You, for example, you model the well that it needs 300 or 400 psi as a drop, while actually it needed 600. So when you didn't model the well good, then you cannot predict good. You cannot predict, you cannot evaluate. So evaluating and getting the benefits from the model depending on how accurate you are modeling your well. So this based on your data. If I don't have a lot of data regarding the temperature, or I don't have a temperature surveys, so I will use it as rough approximation. But if I have data, I can go to enthalpy balance or improved approximation. For the time's sake, I don't have time to go through each one, but later, inshallah, you will have this sure during with OBA or other sessions. Then we have the range full system. Okay, and this is a new here in Prosper. You will find always Prosper is having many versions. This version is 17.5, 13.5. Okay, and always from time to time they have new version. So this is modeling the brine. If you have brine in the well bore, in the annulus, for example, and then we go to the well completion. Is it cased hole? It's open hole. You can use it. You can choose. If I have a sand control method, if I have a gravel bag, pre-bagged screen or not. If you have a sand control method, so then you will use the method that you already have in the well. And then finally, we have the reservoir. For is it single branch or it's a multilateral well? And if you have gas cooling, and when you mean by gas cooling that you have data regarding the relative permeability of the gas, and you have other data from the reservoir that you can introduce the gas cooling here. Okay, so normally this will be the default shape. You will change some of it based on what you actually have. And finally, you have the comment. And I recommend all the time that if you have something, normally if you have a model, you have to write down why you have this model, what is the history of it, anything, because because if you come back to the model and you want to do a new sensitivity, you already remember what is you have or why you done this, or even if you hand it over to another one and he continue in your work, it's good that he understand what's actually going into this model. So this is our option sample. Then the next tab is, which I see is very important tab, is the BVT. The BVT tab. Okay. So in order to remember what is the BVT, let me go quickly through a review about what is the BVT. So normally, as I mentioned, you can model your well depending on is it I have oil and water, or retrograde or and condensate, or wet on or dry gas. Okay. So what is the different? And then we have something we called black oil model and equation of state model. So what is the black oil model? The black oil model, you know that the hydrocarbon or the oil is consisting of many components: methane, ethane, propane, butane, C7 plus, C11, whatever this component, and it have composition of each component. So in black oil, we lump sum all the oil, and we can define it as two only components: the oil and the gas. The oil, the stock tank oil, and the gas. Okay, and we model how the fluid properties are changing with pressure and temperature. So normally, when you go to a new well or in a certain reservoir, you get a sample from this reservoir, and this sample is sent to the lab, and it's preserved with the reservoir pressure. Then this sample, they do some tests on this sample. They change the properties. They change it. They reduce the pressure on this sample, and they see at each pressure reduction what will be the viscosity, what will be the amount of gas, the RS, and what will be the beta O, the formation volume factor. So this is normally, if you have the sample at this pressure, you have what we call solution gas oil ratio. So what is meant by solution gas oil ratio? It means that this sample have a certain gas, but this gas is dissolved into the sample. So we have only oil. Here we have only oil. Then the pressure will reduce until a certain pressure, which is called saturation pressure. When you go below this saturation pressure, there will start some bubbles of gas to evolve, and you will begin to have like two phases: oil phase and gas phase. So while you go down, the amount of the solution gas will decrease because you're already producing some of this gas until you go to the surface. Okay, so this is one of the properties of our black oil, the gas oil ratio. Above the bubble point pressure, you have a certain gas oil ratio and a stable or constant, and then it will reduce as the pressure decrease. So this is the properties we have: solution gas oil ratio, producer gas oil ratio. Another thing that you have also is formation volume factor. So what is meant by the formation volume factor? It is the volume of the volume of the oil at the reservoir compared to the volume of the oil at the surface. So normally the volume of the oil in the reservoir is higher than the volume of the oil at the surface. You can we can imagine it as its shrinkage, because at the downhole you have the fluid, the oil, and it have some gases inside it. So its volume is higher. When you go up, its volume decreased because gas will release, so its volume will decrease. Okay, so the ratio of the volume of the oil at the at the standard condition to the volume of the oil at the volume of the oil at the reservoir to the volume of the oil at the standard condition. This we called formation volume factor, and it's normally above 1. And you see here, because there is expansion here, it's increase, and it's maximum at the saturation pressure. Okay, And then the last one, why I'm going through this, because when we go to the model, you will see that we will have, we will need these mainly these three parameters. And then we have the viscosity. So normally, when the pressure decrease, the viscosity will decrease, as we will see here. As the pressure decrease, the viscosity will decrease. The fluid is not tighter like before, okay? Until it reached the saturation pressure. And what happens starting from this pressure? Starting from this pressure, the gas is evolving out of the fluid. And when the gas evolved, only what is remained is a fluid, so its viscosity will increase as more gas is evolving. Okay? So in Prosper, I'll go back to Prosper. If I go through the black oil model, here I remind you, I choose the method black oil, then I go here in the BVT. You will see that there is an input data here. I have to introduce or have to put it like the solution gas oil ratio, which is from here. It is here, solution gas oil ratio at the saturation pressure. And then I have to put the oil gravity, which already from the BVT report, which is the oil density, and take into consideration always there is here, I can go here and change the unit, whatever units I have. Then the gas gravity, the water salinity, and if I have any mole fractions of CO2 or H2S or N2. And this is always into the report. So I have, based on what I have, I can do it in many cases. Here, if you look, you have here oil viscosity correlation and bubble point, solution gas oil ratio, and beta O correlation. You can go here and choose any correlation you need. But what if this means and what is meant by BVT is matched? Okay, so let's think together. Let's start together to understand what is meant by this and what is meant by BVT matching. I just want to do something. Set all. Okay. Okay. So what is normally here? Now you enter, imagine you have only this data. Okay. And you want to know what will be the fluid property at each pressure or temperature. There are standard correlations that you can use to predict what will be the properties. You have Glasso or different correlations. You can use it for this, and you can have Petrosky or different correlation for calculating what will be the oil viscosity. And why these are important? Because this will give us what will be the pressure losses in the reservoir or what will be the pressure losses in the tubing according to each correlation. But take in your mind that this correlation, if you just use it like this, it will be not accurate. Okay? It will not be 100% accurate. It can be 70% accurate, 60% accurate, 80% accurate. So it's not fully accurate. It will not give you the actual property of your fluid. So if you have more data, and what this is normally the case, and you have a BVT report, so you go here, as you see, you have matched data. So what is this? As I mentioned, normally you have a sample, and this sample, you take it from the reservoir and you preserve its pressure, and then you go and you normally you decrease, you start, for example, from this pressure, and then you decrease the pressure till 300, 500, then you decrease it more in steps, and each step you see what is your gas oil ratio, what is your oil formation volume factor, and what is your viscosity if you have data. And at each step you have this data. You have the gas oil ratio, you have the formation volume factor, you have your oil viscosity. And here you put your data regarding the temperature and the bubble point pressure. So once you already have this, so I can do what I called match. And what is meant by match? If I go like this, it means that I have these correlations, and these correlations have certain parameters. So I tell these correlations, please change your parameters in order to give me values similar to these values. For example, at a pressure of 1000, the model any of this correlation will give you a gas oil ratio of, for example, 200, and will give not 220. So I want the correlation to change its parameter to give me as near as possible to this value and to this value. It's like I'm playing with the correlations to give me accurate as I can, matching to my actual data, to this data, to the data in the table. Okay, and as I have more data, so the matching will be better. I can put until 15 points here. And if you have less data, it's recommended to have like one points before the bubble point pressure, for example here, and one after. One when you have more data, it's better for matching. So as we see here, I do match, and what will happen? You will see that these parameters will change it. Means is it change it to be matching to the actual data. Let's do it again because I want to show you something. If I go here to reset all and reset all, so as you see, these different models, and there was model this one, okay, the Petrovsky, it was modeling the bubble point pressure nearer. These models and these correlations here, they give different values. What did I do here? I matched it all. I changed the parameters of all correlations until all correlations became giving me the same values as the points I entered into the table. Okay, so this is here means BVT is matched. So it's accurate as it can be to the actual data. So now I finish this step. So if, for example, I have a different set of data, I can go to the equation of state. If I go here and put equation of state, okay, you will find it's totally different inputs. I have the name, and I have mole percent, and I have critical. So it's different. It's like I put each composition and how much is the mole percentage of this composition. Normally, we don't go to this unless, for example, you have like cool bed methane, you have dry gas, you have condensate, you have different scenarios. You can go to this, but most of the time, you will find that it's black oil. It's not question of state. Okay, most of the time. It depends also, as I mentioned, on each situation. Then we can go now model our IPR. As you see, it's very easy flow. You start from the option summary, you go to the BVT, then you go to the IPR. In the IPR, I showed you we have a lot of reservoir models depending on the data you have. If I have only P productivity index, for example, let's put it 25, for example, and I have the reservoir pressure. Here I put the reservoir pressure, the reservoir temperature, my water cut, gas oil ratio, and I put the productivity index all here only as a value. And I can do calculate, and it will give me this one, the blue one. This one is the temperature. I can go here and close it, and this is the temperature. It can give me what will be the absolute open flow, maximum flow, and here from the reservoir pressure. And as we see, as the pressure, the BWF decreasing, I have more rate. This will change with changing the productivity index. For example, if it's one, let's do a sensitivity. What is meant by sensitivity? Sensitivity means if I change a certain parameter and I want to see what will be the output. For example, let's go here and let's put cases, and let's put the productivity index here as a sensitivity, a variable, and put, let's see if I have a productivity index of 0.5 and if I have a productivity index of 5, for example. And let's calculate, and you will see here, let's remove temperature to concentrate on it. You see, so this is the IPR in case I have a productivity index of 5, and this is my IPR curve in case of I have 0.5. Okay, so I modeled my PI, my reservoir, my IPR. As I mentioned, it depends on the data I have. For example, let's go to Darcy. If I have more data, more input about my reservoir, I have already, I did a test and I have the permeability. I can put it here. For example, it's say 50 millidarcy, and I have the reservoir thickness, which is, for example, 100 feet, and I have the drainage area. Meaning of drainage area, it is the area it is given normally by the reservoir. The well, it's take or drain oil from how much area. Okay, it depends on the type of the reservoir. It depends on normally it depends on from field to another field. So normally it depends. Some in some fields you can say that it's the drainage radius is 500 feet. In another, it can be 1,000 feet, 1,500. Normally, you all most of the time there is integration between you and between the reservoir engineer, so you can get this data from him. And if you change it into acres, it will find something like this. Okay, so this is the area. In order to calculate the area, it will be pi r square, and you go to the change it from feet square into acre, and then there's something we call Dice shape factor. So it depends on. Let's show you an example here. Like this. For example, where is the well? Is the well here? Or is it circle like this? Or the well is here or the here? How is the shape of my reservoir? What is the effect of this? Because if your well not is centered or there is certain boundaries, it will affect your skin or affect well that would have effect on your productivity index. So that shape is to model where is the well compared to the boundaries of the reservoir. Okay, because something like this is a well here, a well here, a well here, and here, for example, there is a fault. So this tight shape is to making how will be the drainage area and how will be the boundaries and the well position regarding these boundaries. And it's easy. You can go here, calculate it. As I mentioned, for example, here you can say what is the length of the reservoir or the drainage area and your distance. If it's centered, for example, it will be like this. And once you calculate it, it will give you a certain value. Okay. And finally, the wellbore radius, which is the size of the casing. If, for example, I have a 7-inch casing, the inside diameter of it is like 6.8 divided by 2, it will be like 3.1. So you go here, change to inches, go here, and put the wellbore radius. So this is like this. You finished your part of the reservoir model. Normally, you will find that the most two important parameters that will affect or have a high effect on your data is these two, the reservoir thickness and the reservoir variability. And then you put your skin. You can have a skin from the tests you know already, or you can calculate it. For example, here I put it as a value, and I will show another situation like this. Here I calculated it, or I can, this skin, I can go to another, as we see here, models to calculate the skin. In this model, in the mechanical geometrical skin, you will put data regarding the perforation. You can put data regarding the deviation here, because normally you will find that skin is composed of two things. Part of it is the mechanical skin. It's how is the connection between the casing and the reservoir. It's mainly regard about the perforation. And the other skin, it's regarding the deviation, because deviation is always negative skin. Meaning of skin, it's the formation damage. When you have a positive skin, it means I have a damage, a reduction in the productivity index. When I have a negative skin, it means improvement. I have improvement. Like, for example, stimulation or hydraulic frag. These are sources of negative skin, but damage are sources of positive skin. Here we have another model, which is Fitch. You can go through the slides and go through these models. It's another model like Darcy, but here you have introduced something we called relative permeability. Okay. Here, as we see, the same, but here it's relative permeability, if you have the relative permeability curves. If you have done a multi-rate test, you have different rate and different pressures, and then different scenarios here. If you have horizontal well, if you have a multilateral wells, means if you have two layers of the reservoir. Last model here I'd like to talk about, you have spotted some model to model the effect of the completion and mainly the effect of the perforation. Okay, so if you want to use different gun types, you can use these spot models. Anyway, as we mentioned, you already modeled the well, so now your productivity index is already modeled. Now you move to the other part. Remember, we started these sessions with this curve. We wanted these two curves. We wanted to draw this curve, to model this curve, and we wanted to model this curve. First curve, we go to the system, we highlighted it, and then we go to the PVT to put exactly our, to model our reservoir fluids. Then we go to the reservoir and we will be able to draw this curve, this curve. Then now we will move to another curve, which is the VLP. So in order to understand this curve, we need first to understand its component, where the pressure drop is coming from. So as the fluid is moving up the tubing from here up to there are three pressure losses effects. First, this there is the hydrostatic pressure losses because you have a fluid from up here to there. It's have potential energy. If you remember, we have the pressure is H rho G. So there is a component because you have to move the fluid from here to there. So this is first component is the hydrostatic pressure, okay, losses. Then as a fluid is moving through a tubing, it have friction losses. Okay, and finally there's a certain type of losses which is called acceleration, but normally it's very negligible. So come back to this. This is the three component. The gravity pressure gradient or the hydrostatic pressure gradient is depending on the pressure losses, the hydrostatic head of the fluid due to the density of the fluid mixture, and you have the friction here, which is changing or increasing with increasing the rate of the fluid. As we see, normally the gradient is not supposed to be affected by the rate of the fluid, but what is affected by the rate of the fluid and what is increased by increasing the rate of the fluid is the friction factor. So as we see, this curve is the mixture, is the sum of these curves. Okay, but in order, so at the end we come to this curve. This curve is mixture of three components. We said that one of them is negligible, but the most important component are two things: the friction losses, which is increasing as the rate increase, and the hydrostatic head or the gravity part, which is depending on the height and the gravity of the fluid. Then I want to show something that put in your mind the fluid is not like normal two phases. It have something we called different flow regimes, and these flow regimes will affect also our pressure losses. So in well models, in the Prosper or PipeSim or any model, it model the superficial gas velocity and it models the liquid velocity, and it can predict according to this map or different map what will be the flow regime of each fluid. And why this is important, because each flow regime, even if for example I have this well and it has 50% water cut and let's say it not water cut, let's say it gas and oil. Let's imagine this well having 500 scarf per stock tank barrel, okay, and all have the same, and all have the same density of the oil, and all have the same density of the gas and everything. If the fluid regime is different, it means that the pressure losses will be different. Although they are producing or moving with the same fluid type, same completion design, everything is the same. But if the flow regime is different, it means the pressure losses will be different. That's why it's important, a very important part that the model is doing already is to calculate the flow regime, and based on the flow regime, it will be different friction losses. Okay, and you will find that, as we mentioned, something nearer to the BVT correlation, we have different type of correlations. These correlations are used to calculate the pressure drop along the tubing. Again, these correlations are used to calculate the pressure drop from here up to there. And we will find that maybe each correlation will give you different value from another one. For example, I have a correlation. Let's do it before. I just want to show you something, and then we will go in details here. Let's go to the VLP. Here. I have another thing. Let's go. Okay. For example, if I go here from liquid rate, here I wanted to calculate the bottom hole flowing pressure. Okay. %, water cut. Now I'm using Petroleum Expert to calculate this. It gives me the bottom hole flowing pressure will be 1971. Okay, so if I go to another correlation, let's go for example for Fancher Brown, and remember the number here is 1970, and I said calculate. You see, so each correlation will give me different bottom hole flowing pressure. There is a range. So each correlation will calculate the pressure losses from here to there differently. So we will come to the question. So which correlation I will use? If you look at this here, and you find it in the help of the manual, each correlations having like a comment when you use it and what's better. For example, if you don't have a recommended correlation for your field, normally you can use Petroleum Expert 2. Okay, normally you use Petroleum Expert 2. Top. In a minute, we will go to something we called VLP matching, and we will understand better what I can do. But I want to highlight something here, that this pressure losses in the tubing is depending on many factors. Remember at the first here, we said that the VLP is depending on the fluid characteristics and depending on the completion design. So in this example, I'm showing you the effect of the fluid characteristics. For example, if I have a black oil, if I have a fluid, and the gas oil ratio is 500. Okay, so this is my VLP. This is my gradient. This is my pressure losses. If I change it, you will find that the pressure losses decreased. Okay, so if I use this, I can see that we have, or I can model the VLP, the vertical lift performance. Again, the vertical lift performance is the relationship between the bottom hole flowing pressure and the flow rate. Once you increase the rate, you need more BWF to give you energy. And why you need more BWF? To be able to face the friction. Okay, because once the rate increase, it means that you have more friction into your fluid. If you come here, you will find that there is a typical VLP curve. Part of the curve, it is the normal one, that, as I mentioned, as the rate increase, the BWF is need to be increased also to overcome the friction part. But here you have something we called unstable flow. So what is the unstable flow? It is part of the curve that if you produce or try to produce a well at this part, it will not produce in a stable manner, because here the rate is very low. There is a slugging and there is liquid loading and things are not stable. So as we will see, normally when we are producing a well, you have to produce in this part, not in this part. And if there is a well and there's intersection in this part, it means the fluid is unstable and we have a problem. Okay, so we didn't go into how I will model the VLP. Okay, so in order to model the VLP, you need the BVT. We already have it. Okay, and you need to model or to put input data regarding your completion. So you have to put your deviation survey, what is the measured depth is versus the true vertical depth is, what is your completion details, the restrictions, the roughness, anything. Let's go together and let's model it. So remember, we started with the option summary, we go to the BVT, then we go to the IPR data, we draw this IPR. Then here we go, as you see, equipment data, step by step, you can go from up to down. We start at the deviation survey. Simply, you put your measured depth and you put your true vertical depth. And this data, you can get it from the completion engineer, from the drilling engineer, because they have deviation survey. When they drill the well, they have deviation survey. If you have more points, you can have something what we call here filter. You can go here, put all the data here and filter it. Okay. So this is the deviation survey. Then you have, normally if you have choke or surface equipment, you put it. If not, you keep it like this. Then we have go to the downhole equipment. So this is very important. What is the downhole equipment? You draw your well bore sketch. Here in the downhole equipment, you are drawing your well bore sketch. And how this normally happen? You put your Christmas tree. For example, this is from this measured depth. This is a subsea well, okay? And then you put the tubing and what is the inside diameter of your tubing and what is the depth of this tubing and what we called here tubing inside roughness. This is depending on the material of the tubing. You can find that there is standard values if this tubing is carbon steel, if it's chrome 13, if it's new or if it's old. When it's new, the value will be less. When it's old, you will find the value is higher. Okay, then you have to identify your restriction. You have any restriction or not. Okay, I can go with you through. I can remove all of this and 1 second. I want to show you, or even you can go from here. We can go all this. Delete selected rows. Okay, so let's start from the beginning. I want to draw a well. Okay, so let's first imagine how will be this well. Imagine I have this well. This is the casing, and this is the tubing. Okay, sorry for and this is the bucker, for example, and you are producing from this here perforation. Okay, and let's imagine you have a restriction here, and you have up here another restriction for the subsurface safety valve. Subsurface safety valve is a certain valve we introduced in the well in order if we have any problem or anything, it will close. So normally at this subsurface safety valve, there is a restriction. What is meant by restriction? Reduction in the ID of the tubing. Let's imagine that this tubing ID is 2.9 and this casing ID is 4.5. Okay, I just draw this to understand with you, and you all understand with me what I'm gonna do. So here I started with my Christmas tree, then I go to the tubing, I put the tubing, I'm supposed to put the tubing till the subsurface safety valve, till the depth of the surface safety valve. So this till the depth of the surface safety valve, which is normally at 300 or 400 feet. The ID of the tubing is 2.9. Okay. Then I put restriction, which is the subsurface safety valve, and I put how exactly is the subsurface safety valve. For example, it's 2.81. Then I continue drawing my tubing till the next restriction. I continue drawing my tubing till here, till this restriction. So I imagine this restriction at, for example, 200, 2500, and I put also the same ID of the tubing. Then I put my restriction 2.75. Normally it will be less than the upper restriction. Normally in the TALI, in the completion design, you have all this data. And then I put my tubing end. What's mean by tubing end? That my tubing will end here. Okay. So this is my tubing end at, for example, 200, 2800, and the same size of the tubing. Then I will put my casing. Okay, طب normally what is the measured depth here? Normally the measured depth here is what we called mid-perf. The mid-perf, what is called, for example, I have here my reservoir and I have many perforations here. Mid-perf is the depth in between. Okay, this is what we called mid-depth. It will be the datum for me. So let's imagine our mid-perf at 3000 feet and its ID is 4.5 inch. Okay, so now I drawed my downhole. If you want to make sure you draw it rightly, you can go to summary. Okay, let's finish the temperature and then we'll go to the summary. Anyway, let's say mesh. Okay. Then you go to the geothermal gradient. So why geothermal gradient and what is the importance of geothermal gradient? In geothermal gradient, you give how the temperature is changing with depth. Here, my depth at 0 feet, the formation pressure or the atmosphere will be like 60 feet. And at my reservoir, which we said like 3000, the temperature of the reservoir, let's say it will be 150 feet. And here I put a value which is called overall heat transfer coefficient. Normally it's like 8, but if you have data, it is changing as I will show you in minutes, and then done. If I go here to summary, and I can go with draw down hole, you will see here is our well. It is the well, here's the subsurface safety valve, here the restriction, and here our casing. Okay. So now when I go into these inputs, now I'm ready. Now I can draw my VLP. Let's see it. If I go to VLP here, you see this is the analysis summary. This is like the last point. This is when I want to get my output, when I want to do sensitivities, where I want to get my output. If I go here for VLP and put a 120, for example, and go calculate, you will find that this is my VLP. This is my VLP for this wellhead pressure, for this water cut, for this GR. If I want also to do a sensitivity, I go to cases. I go to, let's change according to the gas oil ratio, for example. Let's put it, if it's 200, 1000, 2000. Let's see. And I do calculate. And I do plot. You see here, we have two different VLPs based on my gas oil ratio. This is the curve. Remember, this is the curve that I wanted, this one. This is this curve. So I started drawing this curve, and then I draw this curve, and now I can get this point. It's so easy. How I can get it? Now I can go here. I can go to what we call system. You see this tab, the second one. The first one in flow, if I want to draw the IPR. Okay, if I want to draw the IPR, as we did it, let's remove the temperature. Here, 1 second. Here, remember, we did two scenarios. If, for example, I want I, and the VLB we said, and we have here system. What is meant by system? It means I want to calculate my production rate. If I go to the boundary and I put, boundary pressure means the wellhead pressure. If I put it like 100, I can calculate, and now I have the rate. It's a high liquid rate because we put a high productivity index. If I go there and reduce this PI, make it 5 or something, I show two scenarios. And I go to system, we will see the rate reduced. Okay. Type. If, for example, let's imagine I have this well and I started my liquid rate production with 8,500. And I know that after months, my water cut will increase from 2 to 100, or from 2% water cut to, for example, 80% water cut. And I want to know what will be the rate. It's easy. I can go to cases. I can put here water cut. I can put it here, 80, for example. And I can do calculate. And you see, it didn't change so much. Top. Let's imagine another scenario. Let's imagine that I know that by some time the reservoir pressure will decrease. What is our reservoir pressure now? Our reservoir pressure now is 3,290. Let's imagine that the reservoir pressure will decrease to 1,500, and I want to know at this time what will be the rate of the well. It's easy. I can go here. I can go to calc to the reservoir pressure. I can put it as 1,500. Okay, and another scenario like 2,500, and I can do calculate, and I can see what will be the rate at which time. For example, if the reservoir pressure reduced to 1,500, this will be my rate. If it's 2,500, this is my rate. What if it's decreased to more rate? What is, for example, 800? Okay, let's see, for example, I want to know what at which reservoir pressure my fluid will be dead. My well will be dead. It will not produce. I can go here, for example, I can generate from 300 till 1,000. Okay, let's put it like 8 points, generate. You see, like between 300 or like less than 400 psi, my well will be dead. Let's see, as when the reservoir pressure was 400, you see it was producing like 370. But when the reservoir pressure is like 300, it's dead. So it's something in between. If you look at the, let's do the plot to understand it more. You see, we have different VLB and you have the IPR, because what is changed is the reservoir pressure. So what's happening that the IPR is starting from different point, and through all this point there is intersection between the VLB, this one, and the IPR until we reach this point. Okay, let's show it again in less point to make it more obvious. Let's point, for example, 300 and 500. Okay, and let's calculate and let's plot. So if you look at this, when the reservoir pressure was 500 here, this is my VLP and it intersect at this point. Okay, but when my reservoir pressure was 300, there is no intersection. So my well will not produce if the reservoir pressure is 300. Okay. Sure, you can do many sensitivities. You can, for example, change it in another scenario. Yani if, for example, I increase the wellhead pressure, it's 500. Let's see. At this scenario, you see this is my VLP, it's moved up and it cannot produce at all with 500. It even will not produce even if the reservoir pressure was 1000. So let's do this again. Let's go for reservoir pressure higher. Let's go to, for example, 1000, 1002, sorry. 1200, 1400. Let's see. I think it would be something in between those. You see, so when it's 1000, it's not producing. When it's 1200, it's producing. You see, so when the boundary pressure changed, when the wellhead pressure changed, the well is dying at higher reservoir pressure value. As I mentioned, you can play with anything. You can even play with the tube, with the completion. You can change the completion size. I can go here and I can go with the downhole equipment and I can add a new scenario. Let's say, for example, rather than the tubing size of, rather than the casing size of 4.5, let's change it into 7-inch casing size. You see the effect. And let's change the tubing also. Let's change it. Let's make it 4, for example. 4, 4. Let make 6, 7. I'll put this, for example, 3.81, 3.75. Let's see what will be the effect. Okay, so this is one scenario, 7, and another scenario is 4.5, the initial scenario. Okay, as it is. Okay, let's see the difference between them. Okay, so now I changed my downhole equipment, I changed my completion, and I want to see what will be the effect in each scenario. Okay, 1 second. Let's also make a reservoir pressure of 1200. Okay, to see the effect. Okay, and let's calculate. So as we see, when the reservoir, when the equipment is 4.5, this is my rate, 1200. And if I increased, there is no much increase in the rate. I can even go here in sensitivity plot. This is the liquid rate, and this is the downhole equipment. This is the first scenario. This is the second scenario. There is increase, but not much increase in the rate. It is 1221 to 1232. So is the increase in rate justify using wider tubing? Because wider tubing means increase in the cost of the tubing. Okay, so this thing, I can add another thing to make it also clear. What if, for example, I choose the very thin tubing? Let's see if I choose tubing size of 1.9, for example. Let's make this 1.9, 1.81, 1.9, and reduce this to 3.5. I just want to show you a big effect on the production, to show you how with modeling we can model different scenarios. You see here, for example, when I used thinner tube, it changed dramatically. For these two cases, the rate wasn't changing too much, but when I used this tubing that is thinner, smaller size, rather than I'm producing 1200, I'm producing 800 barrel. Okay, so this is another thing. Okay, so let's get to a very important thing, which is tubing correlation comparison. I mentioned that we have different types of correlations. Okay, we have, as you see here, Dance and Ross, Petroleum Expert 5, Petroleum Expert 2, different types of correlations. So which correlations I can use or is better to use? So normally we have something we call tubing correlation comparison. If I go here, if, for example, I have a measure depth and I go to this well, and in this well I have a test, and this test told me that the liquid rate is this value. Okay, and at that time this was my wellhead pressure, and at that time I go inside the well with a gauge and I put it at a certain depth. And at this certain depth, this was the recorded bottom hole flowing pressure. Then I calculate. Second. Because I changed the model. Okay, let's change it. Maybe the values will not be the same as, but let's see. And Sandros, flower. And here I choose different correlations. And then I do calculate and then plot. Okay, clear all. Let's put petrol export 5. Financial plan. Here I change the correlations that I want to plot. And in a minute, I will tell you what's the meaning of this. Cancel. And Sandros qualified. Maybe because the data, I changed the data. So let's. Okay, let's get it from another scenario. I don't know what is the wrong here. Well, I will give you it is from another side. Here we have something we called VLP IPR matching. If we go here, so what is the point of this value? Here, imagine I have, as I mentioned, I go to the well and I have a test and I have a gauge. So I put here my test date, for example, let's be 5th of September of 2025. And I put it here that it's a well test. Okay. Then I put my tubing head pressure from the test. I put my tubing head temperature, water cut, liquid rate. Let's put it, for example, this rate. The depth of the gauge, where was the gauge, and what is the pressure I was seeing at this time. Okay, my reservoir pressure, my gas oil ratio, all this is supposed to be in the test. Then, based on this, I estimate my U value. So what is meant by this? It means that I had a well test, and from this test, the temperature of this fluid was like this. It was like 120. Okay, and from this, when I go to estimate U value, it means that the model calculate a new U value, a new heat transfer value. To make it more understandable, remember, here we have something we call geothermal gradient. Here we go to the geothermal gradient. You put what is the temperature at the surface and what is the temperature at the formation here. And you put here a value at the beginning. It was 8. It means overall heat transfer coefficient. It's like you think, or standardly, it's supposed that the well will lose heat. The fluid as it's moving from down the well up to the surface, it will lose heat at a certain rate. Okay, this rate is 8 BTU per H per F2 square per F. Okay, this is the rate that the fluid as it's moving from down to up, it will lose its temperature, its heat. Okay, this is if you don't have any test data. But if you have actual data, you already have actual data, you already have a test, a valid test, and in this test, you have measured the wellhead temperature, so you put this temperature. Now the model will give you a better estimation. You will give you better calculation of the U value. It means that the model, based on your data, suggests that it is supposed that the U value, the transfer or the loss of the heat, is this value, not 8. If you put it like this, it's better. Why? Because this means it will the model will give you better modeling of your temperature changes. Because we mentioned before, the temperature is very important because the fluid characteristics are changing with temperature. And as the fluid changes with temperatures, it means that the pressure losses also will changes. Remember, at the end, you want to model your well performance regarding the pressure losses, and you want to do it as accurate as you can, so you can predict any changes in an accurate way. So this is the first part. Then we go to correlation comparison, the part that I tried to match but it didn't work. Maybe it's working here. Then here we put our first node, our water cut. As I mentioned, the data, this is the test data, and this is the data of the gauge that is supposed to be down. And here, this is the correlations that what is meant by this. I have a gauge downhole, okay? For this test, for this rate, it measured this value. In the same time, I want to see each correlation, what will be the values that is calculated by the correlation. Okay, if I go to Duns and Ross here, petroleum expert, let's just have 3 correlations and Fancher Brown. Okay, and I set calculate. Okay. Okay, maybe something regarding the license of this of the model of the Rosbar I have. Okay. Let's see if it's working or not. Okay. Okay, anyway, if you look here, so this is our data. You see, this is our data. This is the pressure, and this is the measured depth. So at 3000 here, I put the data that the pressure is 1800. But in the same time, if I'm using Fancher Brown, it shows me that no, the pressure should be like 900. If I go to Duns and Ross, it shows me the pressure here is supposed to be 1200. If I go to this correlation between expert, it shows. So what does it mean? It doesn't mean that the pressure that I measured is very high compared with the correlations. What is the standard? What should I do? Normally, you have 2 correlations, Duns and Ross and Fancher Brown. Fancher Brown is a correlation that is the correlations that is give you the least pressure losses, and Duns and Ross modified give you the highest pressure losses. So if my data are right, it is supposed that this value is supposed to be here between these 2 correlations, between Duns and Ross and between Fancher Brown. So what this means? This means this data is not right. It means that either the liquid rate is not right, or the measured PWF is not right. Okay, let's do a change. Let's change the liquid rate. Imagine that I have a problem in the test, and this liquid rate is suspected, and the liquid rate can be, for example, 3000. No, it's even not like this. Let's put it. Okay, so it's seeing that it needs. Okay, this is what I meant. So for example, if the rate is higher than this, okay, you see, this is my point here, and this is Duns and Ross modified, this blue one. If Fancher Brown, it is here also, petroleum expert 2 here. So if I go another way, I put the rate here 1200, but the pressure is different. Remember, I changed the data for you so that you can go step by step with me. So if I go here, Duns and Ross modified, and here Fancher Brown, yes, this is what I wanted to show you. So if you see here, this is the data, and this is the curve of Fancher Brown. So the data expected a higher pressure losses than Fancher Brown, but Duns and Ross modified, the correlation is expecting higher production losses than this. So when my data is between these two lines, this means my data is to some extent are accurate. So this is the first QC check I did. The second one, what is it to, is to do something we called matching the correlation. Matching the correlation. So what is matching the VLP means? It means that we have here parameters. Okay, here we have parameters like in the BVT, you had parameters for each correlations. Here we have parameters, parameter 1 and parameter 2. These parameters are used to calculate the pressure losses with the correlation. If I do something we called match here, it means, let's choose a test and I do match. What does it mean? It means that it will change the parameters of the correlation to match my test. Okay, it means these numbers are very high. Okay, it means if I go like this, if I go again to correlation comparison, okay, and if I calculate it, you will find that the correlations now are matching my data here, here, here. You see, the correlation is calculating the same pressure losses as the data I entered. So here what I did, like I did in the BVT, I changed some parameters or some calculation inside the correlation so that it matched exactly my data. So it's like I increase the accuracy of the correlation. So again, what happened? I started with, let's reset everything. So I started from this VLP IPR matching. I put my test data. I go to estimate the U value. Then I go to correlation comparison as a QC to see where is my data compared with the, oh, this is my test data. 1 second. I get it. I did calculate. Yes, this is my test data here. This is functional Brown. This is what is functional Brown? This is functional Brown. Second. This is functional Brown here. This is Duns and Ross. Oh, I didn't calculate it. That's why. Okay. This is okay. This is Duns and Ross here. So with Duns and Ross correlation modified according to this rate and this wellhead pressure and this data, I'm supposing to have a BWF down 1180, but the actual data is 1100. If you go to Fancher Brown, I'm supposed to have, this is the one which is calculating the least pressure drop. I'm supposed to have 890 psi. So I'm first, I look at my data and now I'm sure it's between them. Okay. So now I go to Petroleum Expert. Okay. I can use Petroleum Expert, Duns and Ross original, Petroleum Expert 3, Petroleum Expert 5, depending on each situation. But after I finish this, I can go to what I called match VLP. If you look at the parameters, you will see that their parameters are all, the parameters are all 1 and 1. If I go to Duns and Ross, Function Brown, and Petroleum Expert 2, I can do what I called match. It means, yes, I need to check the test. I can do what we call match, and now the parameters are changed, which means if I go here in the correlation comparison and I did calculate, you will find that they calculating the same exactly BWF as my data. So now I finished the things. The last thing is to do what I called VLP IPR matching. What does it mean? I can use any correlation of this. Okay. Let's use this. I calculate. Okay. It's like I'm seeing the VLP and the IPR. So we have something we called adjust IPR. Okay, what this means, it means that based on the data I entered and based on the server pressure, they see that it's not supposed to produce. So if I go there, let's put it like this, and I go to adjust IPR. Okay, it means, for example, I was putting that my PI value is 5, but based on the test data that I entered, it's not 5, it's 6.3. Okay, so here I first improved the temperature values, the losses of the temperature. I choose or changed choose the right correlation and changed the parameters of the correlation. Then the last thing, I adjusted the productivity index based on actual tests. It's like at the beginning I had the reservoir data and I put the PI here as 5, and I calculated the PI based on this 5. Then I put the well in production, and then I had data from the well. So I used this data and I did what I called adjust IPR. And when I adjusted IPR, or told the model, please tell me what will be the PI to give me this rate. And I did enter, it gave me another value. So now I have a better matched model. Okay. So here as we see, we started from the option summary, we go to the PVT, we go to the IPR data, deviation survey, equipment data, and the analysis summary. The last thing that I want to highlight with you today is what if I want to add an artificial lift method and I want to do a design. So I can easily go here. I can go to the artificial lift. I can go the method. For example, let's imagine I have ESP. I can use ESP. So I have two scenarios. One scenario that I already have an ESP installed, and I want to put this data of this ESP, and I want well based on these ESP data to calculate my rate. So I can go here to the ESP input data, and I have this data. I have, for example, what will be the depth of the pump. Let's imagine it's 2,500. What is the frequency operated? So this data from the pump already you know it. What is the OD of the pump? Okay, if you have a separator efficiency, if for example it's 80%, what is the number of, okay, what is the voltage of the surface? All this data is supposed to you have it. Okay, so yes, number of stages, current pump. Here you have the catalog. For example, imagine I have this type of pump, ESP 4 inches. If you go here, you see these different vendors of pump, and each here, this is the size of the pump, and here, this is the optimum rate for the best efficiency. And then you have the motor, okay, and then you have the cable. All this data, suppose that to be with you, all this data, if it's exactly a pump that's already, okay, ESP number of stages. Here, because the scope is to introduce to you what will be the input data and how I can do a quick design. So as we see, it's just an introduction. Okay, so this is the data I needed to model my pump. I put the pump depth, I put the operated frequency, I put data of the pump, I put the number of stages, I put all this data, and I use this data to calculate. Okay. Modeled. Okay. So here I need for the downhole equipment to define, because I introduced a pump, it's need to define what will be the casing around the pump. Let's imagine it's 7-inch casing. Okay. Here it's normal. If you have done something error, it gives you what's exactly. Aha, yes, I put it quickly, so I didn't read it well. This is the casing inside diameter, and here is the tubing outside diameter. Let's say it's 3.5, 3.5, and 3.5. Okay, done. Let's see. Yes, now there's no issues. Okay, probably I didn't enter the data right of the pump. Okay, but one second, I had another file. Yes. Okay, this is another pump that I already entered with right data. So as I mentioned, I enter the data here of the actual data I have, and then I go to system, and I can let's remove the cases. Let's do calculate. I can calculate what is my rate with the pump, and I can then changes. I can put different scenarios. I can, for example, put for the pump what will be the frequency, pump frequency. Operating frequency. For example, different operating frequency, and I see at each operating frequency what will be the rate to. Okay, if I, for example, I have a certain power source and I'm operating the pump at a certain frequency, and there's a changes in the frequency, and I wanted to know what will be the new rates. Okay, the same as you mentioned, as we mentioned. And here, if you look at this side, you can see different data. You can see the liquid rate, you can see the bottom hole flowing pressure, you can see also data regarding the pump intake pressure, the pump discharge pressure, okay, the frequency, the power generated, the pump efficiency, everything regarding the pump, you can have it here. And there's also sensitivity plot here. You can go to variables and you can change and see what will be the difference. As we mentioned here, for example, 1 second, calculate sensitivity plot. What happens? Liquid rate. Okay, as we see here, as the operating frequency changes, my liquid rate also changes, it's increasing. Okay. Now, what if, for example, I want to do another design? It's so easy. I can go here, either from this here or here. I can go to design, or you can go here from ESP design. Okay. So normally what happens? You can go here, ESP. So normally when you start the design of the ESP, you start with highlighting what will be the pump depth. So normally it's as near as you can to the perforation, and it depends on the deviation of the well. So sometimes the well's deviation or the dig leg severity will keep you putting the pump at a certain depth that you cannot go more than this depth. So imagine in our scenario, you have already know that pump depth will be at 2,500, and according to your sources, you have a certain frequency, okay? And you have the pump OD. The pump OD is depending on the casing ID. Normally, each pump is having a certain clearance between the pump OD and the casing. For example, if you have a 958 casing, so you can go through it with 7-inch pump, for example, or 658 inch. But if, for example, you have a less size of the casing, it means that you will have a less size of the out of the pump. Okay, and when the pump size is higher, normally or logically means that the rate will be higher. So at this scenario, we have 4.5. Let's imagine that the maximum of the pump is 4 inch. Okay, the length of the cable, it will be till the surface like 2,500. What is the separator is efficiency? Normally, when you put the design, it's make it 100%. So normally, what will be your design rate? So normally, I go to the pump and I know that I want to produce 2,000, 3,000, 5,000, whatever my rate. Okay, let's imagine it's 2,000. What is your water cut? What is your GOR? What is your wellhead pressure? Okay, what is your pump friction wear if you have? What is the casing diameter at the motor? Let's put it 5. And you calculate what we call pump duty. If you do like this, okay, you need me to enter a pump wear factor. Let's put it 0.1. And you calculate, okay, here I did a mistake. I put that design rate more than the actual capacity of the well. So it's get here, fluid can't reach the pump at this rate. So this rate is not realistic. So I can go with less rate and calculate. Also, this rate is not realistic. Sorry. Let's decrease the rate. Yes. When I decrease the rate, it's calculated anew, as we see here. This is the pump duty. It's give me what will be the bottom hole flowing pressure, the frequency, the discharge rate, give me all the data I need. So using this data, I can go here and choose which pump will be the optimum pump, what will be the motor, and what will be, and I can get from here the final results, which it can be the number of stages, the bar required, the efficiency, and all the required data. So this is what I wanted to be and to say today, and I hope everything was clear. It was quick and it was I couldn't go to everything because things where to there's a lot of things to go deep inside. So if you have any questions, please let me know.
Thank you, Engineer Ahmed, for this fruitful session. Please, attendees, write your question in the chat box if you have a questions. Engineer Ahmed, we have already questions during the session. Can you check this?
Oh yes, so on said what is the name of software? It's Prosper, where we can. Okay, I didn't see any questions. It's just they are asking. I didn't see any questions. Now, okay, now this question started. You are all welcome.
Okay.
Okay, why does the water cut and GOR have effect on the IPR curve? They have effect, but not very high effect. They have effect, but not very high. But why? I will tell you this why. Because if you look at the IPR curve, you will find it's something like this, right? The IPR curve is a straight line here, and starting from this point, it is starting to become a curve. Okay, why it's curve at this point? Because starting from this pressure, which is the saturation pressure, this is the pressure where gas is starting to produce. What does it mean? It doesn't mean from here to there, only I'm producing oil. But starting from this point, I'm producing oil and gas. So if the water cut increased, what does it mean? It means the amount of gas will reduce. So this curve will change. Okay? So water cut and gas are changing because of this point. Because is suppose that it's a straight line, and because of the production of gas is doing this curve. So the GOR or the water cut will have effect on this curve. That's why it's changing. But you will find it's normally it's not changing above. It always changing below this saturation point. Okay. Is it clear or not? If it's not clear, I can say it again, no problem. Thank you all. Thank you all. Okay, the core of it is, I will tell you. If you go, for example, 1 second. How we draw this curve or this line? Okay, for the part above this point, we call this using Darcy model, where you use the permeability. Okay, if you go and see Darcy model, it's K delta B over L, Darcy model. Okay, but below this point, below here, it is not the permeability. It's another thing introduced, the relative permeability. Because starting from this point, you have gas, you have oil. It's imagine water is not here now. You have oil, you have gas. So starting from this point, in order to calculate this, it's calculated, for example, if you use Vitkovich or other models, it's calculated use the relative permeability. So the relative permeability will change with it changing the water cut or changing the oil percentage or changing the gas percentage. That's why adding gas oil ratio different or adding water cut will having this effect. Okay, I hope it's better now. You are welcome. Before, is the IPR the same way as lifting submersible pumping at the super condition? Is the IPR performant in the same way? What's the meaning of the IPR performant in the same way if you have a lifting system such as submersible pumping? I don't understand. I understand now. Okay. Yes. IPR is not affected by the type of the artificial lift. Okay. Whatever the artificial lift you are using, you have like two components. IPR, you are modeling whatever the submersible or the different artificial lift method. And then the VLP, no, it depends on the artificial lift method. VLP will change with changing the artificial lift method. Okay. So, and the reservoir conditions such as active aquifer, this will affect the reservoir pressure. If you have مثلا active aquifer or you have deflation drive reservoir or whatever the type of the reservoir, knowing what is the reservoir mechanism will affect your reservoir pressure. So before the software, they were modeling it using Excel, using the correlations, but they could do it the same, but it wasn't very accurate like now, and it would take more time. So the benefit of models that it make it easier, it make it more accurate, and it decreased the time taken to do the modeling. Okay. I wanted to ask how this can be correlated with production forecasting. Exactly, it's you remember at the first we said that benefits of the one of the benefits of the modeling that you generate what we call lift curves. What the meaning of lift curves? If you go to Prosper here, there is something called here generate for gap or VLPs. Let's imagine generate for gap. Here I put different wellhead pressure. I draw different VLPs. To understand, if you are doing a reservoir simulation and you have 100 wells, okay, and you want to predict what will be the rate for each well, it means that you need 100 model to be running with the simulator at the same time. So this is not applicable. So what normally happens that you have a well model, you calculate what will be the rate for different reservoir pressures. For example, I have a reservoir, the pressure now is 2000 and it will be reduced till 1000. So I have 100 well, I bring these 100 wells, I do cases, okay, from 1000, from 2000 psi reservoir pressure to 1000 psi reservoir pressure. And I calculated the VLB for all these cases, for the 100 wells. And then these cases are taken and they are inputted into the reservoir, into the software that is doing reservoir simulation. Okay, and the calculation are done because it's not easy or it cannot be done that you cannot doing the reservoir simulation and at the same times the models are doing simulations. No, you are doing the simulation with the models, the well models, then you extract or export these results from them as results, VLPs as results, and then you put it inside the simulator software for the reservoir, and then it continues its work. Okay. Any other questions?
I think this is the last question, Engineer Ahmed.
Okay.
Okay, thank you, Engineer Ahmed, for this great session.
So much.
And thank you all for attending this session. If you have any questions, please write it in the chat box or on the WhatsApp group, okay? For any inquiries related to the session. Okay, thank you all.
Thank you all. Goodbye. Have a nice
Goodbye.
night, inshallah. Bye bye.
Inshallah. Bye-bye.